see if we can install traffic signals within our project. We had to minimize environmental impacts within the project footprint, protect the storm drain that was just north of State Street, and provide a roadway for connectivity between State Street, the existing State Street, and so now what I'll do is I'll pass it over to Gonzalo, who'll talk about our environmental analysis.
All right, thank you, Daniel. As you guys know, environmental analysis and approval is a crucial step for every project between stage and start construction and design. It actually can be a really long and tedious process. They can delay projects from months to years. So I'm pretty sure all design professionals, you guys know that. And of course, going to explain the process that we got for our project. And we must start with NEPA, the National Environmental Policy Act. Pretty much, they do all the procedures and guidelines for every project in the nation. Now, every state has their own guidelines and environmental procedures. In our case, that would be the California Environmental Policy Act, or CEQA. Now, in order to follow this guideline, we must have a lead agency. In our case, for our project, that would be the City of Montclair. So they have to make sure the consulting firm follows all the procedures and guidelines. And after this, actually, the first step we must take is to get into the California Environmental Handbook. This is the rotational project, the bulk catchment, and the purpose flow. Now, California actually has two main procedures for the environmental analysis. One is for the in-state highway system. The other one is for the projects of the state highway system. So projects are of the state highway system. Therefore, the main procedure, the main environmental analysis we must do is called a PES. In other words, preliminary environmental study. We did this study completely throughout the whole year. And let me actually explain to you what the PES is. PES analyze all the environmental effects and impacts that the project will have in the surrounding areas. We actually, these are a couple of the studies that we actually did throughout the whole year, such as noise, biological resources, air quality, community impact, cultural resources. So we analyze pretty much every area, environmental area for this project. Now, after doing the studies, we were actually came out with the conclusion. So the project, actually the form itself helps you classify this project under NEPA. So now project is actually categorically excluded from NEPA. The main message of this is that actually the project will not have any environmental impacts, significant impacts or effects on the surrounding area. However, we still need to follow the CEQA guidelines. Therefore, CEQA actually, we identified 4 of the studies that need to be done, which are noise, biological resources, air quality, and community. Now I'm going to head it up to Brian who will talk about separation of community.
Thank you, Gonzalo. Now, we were tasked with the design with grade separation, not just a road bridge or a railroad trench. So the first thing we had to do was identify all the different possible alternatives that would satisfy our criteria, and then we performed a qualitative analysis and determined which one would best suit our design. This is the existing conditions, and as Daniel stated earlier, there's lots of congestion and a safety hazard, and that's why the city has told us we need to make this grade separation. The first option we looked at was the railroad trench, which is essentially digging underneath the existing Monte Vista Avenue grade. And this trench would extend for nearly a mile in each direction, and it would affect the rail traffic. And if the railroad is affected and they deny our project, it won't be built because this is on railroad property. So this is a bad alternative. The next option is similar. So railroad flyover. It would also extend for nearly a mile in each direction, and would also heavily impact the railroad, and therefore we cannot pursue this option. The next alternative we looked at was the roadway underpass, and this is simply digging underneath the railroad in lowering Monte Vista grade. And this option would require 2 railroad bridges, one on the north UPR line and one on the south line. In addition to the effects on the railroad, it would also affect nearly all of our underground utilities, making it a very difficult and complex alternative. Our next alternative, and the one we selected, is the roadway overhead. This is just a simple road bridge over the railroad right-of-way, and this affects the railroad the least and our underground utilities the least. So that was our selected alternative, and it also We minimize the impacts of our railroads so they won't deny our project, and it is the least expensive with only requiring a single bridge. That brings us to our final vertical alignment. This alignment was driven by the very important requirements that the railroad has provided us that we must maintain a 22.5-foot vertical clearance over the railroad at all times. And we added that to our own constraints of meeting the existing Monte Vista grade at Holt intersection in the north and the fire station in the south. That left us with a very steep exit grade of nearly 7%. In order to have an exit grade of greater than 5%, we need to either have meandering sidewalks or landings on our approach. Our site was best suited for meandering sidewalks. Now we will discuss the State Street connection alternatives. This is if we didn't worry about State Street at all, we would end up closing it, and this does not meet the City of Montclair's requirement of maintaining connectivity. So we must do something with State Street. The first alternative we looked at was to raise State Street to the new Monte Vista grade. And this alternative would be costly because it required lots of fill, lots of retaining walls, and would also affect some underground utilities as the added soil loads. So, and it is more expensive in comparison to our next alternative, which is simply to reroute State Street to the south. This has a disadvantage along with the last option of we still have an at-grade crossing between State Street and Monte Vista, which is not the best for traffic. Our next alternative solves that problem by building the Monte Vista Bridge will extend over the existing State Street, and then we will build connectors to the south to maintain connectivity. Now, our traffic analysis showed that we don't need a connector on both sides. A connector on a single side would suffice for the traffic flow congestion requirements. And after taking a look at both sides, we found that the west side was less developed land and would be cheaper to build on. That brings us to our final design, west side connector, and this has the additional advantage of directly connecting the fire station to the new State Street, so the emergency personnel wouldn't have a reduced response times. And now on to the traffic analysis.
Thank you, Brian. So since we selected our State Street connector alternative to connect it on the west side of Monte Vista, we were able to implement two traffic signals in our project. I'm going to take you to our existing conditions first. So right now at Monte Vista, we have an unsignalized intersection between Monte Vista Avenue and State Street. We have on the eastbound and going east to west, we have two stop signs, as you see right here. And going north to south, we have free flow traffic. However, just because we have free flow traffic doesn't mean our traffic is free flow indeed in this area. From our analysis, we saw that we had over 80 seconds of delay, which yielded a level of service of level of service is basically a grading scale for the traffic flow in this particular area. So us getting an F in this area means we have the worst amount of traffic possible. So now what we propose to do is install two actuated uncoordinated signals at the existing State Street and the State Street connector intersection, and also the State Street connector and the Monte Vista Avenue intersection. So on the Monte Vista Avenue and State Street connection intersection, we brought it down to about 28 seconds of delay, which yielded us a level of service of C, which is ideal for a condition like this. We also, for the existing State Street and the State Street connector intersection, we brought it down to about 16 seconds of delay, which gave us a level of service to B, which is also very good for a condition of this type. Now what I'll do is pass it over to Eddie Vega, who will discuss our overhead structure.
Once the civil team identified that we would be using an overhead bridge, the next step for the structural team to do was identify which bridge type we would use for this structure. With that, we identified several alternatives. The main bridge types that we did consider were different beam girder bridges and box girder bridges that use different combinations of steel and concrete. For these alternatives, we defined several criteria, and these criteria included cost, aesthetics, which are fairly self-explanatory, construction requirements, which included considerations like if the bridge type needed false work, as we needed to, as the railroad clearance was one of our most relevant constraints. And another criteria was the suitability to geometric and physical conditions. And what this included was whether the bridge type we were looking at would be able to meet the span lengths that we were expecting and the loading conditions that we were also expecting. So with these criteria, we performed a qualitative analysis using our evaluation matrix. To show how this matrix worked, we assigned different weight values for each of our criteria and then rated each alternative as either poor, neutral, or good. When we did our first run through of this evaluation matrix, we couldn't eliminate too many of our alternatives, and we came to the realization that our designability would be one of our governing criteria. But that, what I mean by designability is that as students, we unfortunately are not fully capable at this point of designing all the alternatives that would naturally be considered in a grade separation of this, and so we needed to take this into account in our evaluation. So once we did add this into our matrix, it helps us focus in on a specific alternative, that being the composite bridge. And with that, we are recommending that our selected bridge type as a composite steel girder bridge with a reinforced concrete deck. And what that is that's a steel girder bridge with the top flange of the bridge studded to the concrete slab. The main rationale for us selecting this bridge type was that it met the geometric and physical needs of our project and that it had the added benefit of having less impact on the railroad due to the lack of false work as compared to some of the other alternatives we were considering. To talk a bit about our design methodology, we approached it from top to bottom. We first started with the design of our deck and girders, followed by the design of our bent cap. Continuing downward, we designed our bent columns and ultimately concluded our design with our pile caps. The actual design of the piles was taken by our geotech team. For our seismic design, we performed a pseudo-seismic analysis in which we calculated the period of our structure and used that with the response spectrum as developed for our site to determine which lateral loads we would need to design for it. For our standards, we used the Caltrans Bridge and Highway Design Manuals. To talk a bit about our span configuration and structural system, we are using a 3-span bridge with simple spans. We designed for lateral resistance at both abutments and both bends. To highlight some of our most relevant constraints, we have the clearance requirement for the railroad. That was relevant as it did affect early on in our project when we were deciding the alternative that we would use. Another relevant constraint we had was the railroad right-of-way, as we tried to minimize our impact on that right-of-way. Another relevant constraint we had was the existing utilities. As you can see near our Bent 3 location, we have a fiber optic line as indicated by the yellow and a petroleum line as indicated by the red. When we initially proposed our span configuration, we had 3 equal spans, but the problem with this was that it led into a direct conflict between this Bent 3 and these utilities. And so what we decided as a structural team was to actually move our Bent 3 about 10 feet south to meet the clearance requirement for these utilities. So in this case, the existing utilities actually governed our structural design. Another relevant constraint was our existing channel. As you can see near Bent 2, we have an existing channel. And what we needed to do for this case was accommodate or mitigate the fact that this channel was not designed for the extra force that would result from this bend, and this issue will be discussed further by our geotech team. These different scenarios demonstrate the interconnectivity between all the disciplines in this project and show that interaction between all of our teams on this group, this project, were integral for a successful grade separation. With this, I will pass it to Joseph Esqueda, who will talk about our completed design.
Thank you, Eddie. Our bridge was 279 feet long and 79 feet wide. It had a reinforced concrete deck that was 9 inches thick. It had 9 steel girders that were 6 feet deep, spaced 9 feet apart. The girders have gear keys in between them to resist to transfer the lateral loads. Those girders are supported by a bent cap that is 7 feet by 7 feet by 79 feet long. The bent cap is supported by 3 5-inch diameter columns, bed 2, or 5-foot diameter columns. Bed 2 is 34 feet high and bed 3 was 24 feet high. The 3 columns are supported by pile caps, which are 7 cubic feet. So our final configuration was, we had 2 abutments at each property line with 2 beds. The first span was 73 feet, the second span was 83 feet, and the third span was 122 feet. Bed number 2 interfered with the water channel, which will be under the geotechnical considerations. I'll get into that then.
I'm going to be talking about the geotechnical design and how the decisions of other groups affected the geotechnical design. To give you a background of what the geotechnical team did, we first performed a site investigation background to investigate the subsurface conditions. As Eddie mentioned, for a pseudoseismic analysis, we had to develop a seismic response spectrum so we could perform that analysis. We had to develop and design a retaining wall structure to support the roadway approaches, and we had to design the bridge and abutment foundation systems. To give you a brief overview of the site conditions themselves, it's primarily a silty sand. You can see with these soil parameters right here. No groundwater was encountered at the site, and the historic high is greater than 100 feet, which means liquefaction is not a problem. As you can see by the soil profile here, it's varying layers of sand with a silt layer at approximately 55 feet below the grade. I'm now going to talk about the retaining wall design. As Brian mentioned on the civil team, our proposed solution to the grade separation is to have the bridge fly over the railroad. And so we need retaining wall to support that. We chose an MSE wall, which you can see on this picture on the right. And the reason we chose MSE wall is for its low cost as compared to other types of built-up walls such as concrete canister walls. The picture on the left is our final design for the retaining wall structure itself. And we used the Caltrans bridge design specifications to design that for both internal and external stability. We're using reinforced steel strips in the form of an extensible steel reinforcement. And the design was obviously designed for traffic loading, earthquake loading, and of course the weight of the backflow itself. Now I'm going to hand it over to Esteban, who's going to talk about the foundation systems.
Thank you, Zachary. The geotechnical team was also responsible for the selection of the foundation systems. Now, as you can see here, what we ended up selecting were CIPH piles. That stands for cast and drill pole. This is one common type, although there are two specific types designed, one typical of the abutments and one typical of the vents. As you can see here, the vent foundations were 65 feet deep with vertical capacities of 600 kips, and the abutments were 80 feet deep with vertical capacities of 800 kips. The way we designed these were according to the Caltrans bridge design specifications, and we also conducted a pseudo-seismic analysis for lateral loading. What you can see here is a typical section. And you'll notice the 3-inch concrete cover with a reinforcement. This image is a foundation plan which shows our abutments here and here, and our vent locations represented in the center portion. This shows the arrangement of the shafts along the abutment, which is typical of both. And this shows the arrangement of the foundation systems of the vent columns. Those are individual pile caps. And one important thing to note here is that these are arranged in groups. Shafts or any foundation system arranged in groups helps to drive lateral loading capacity. So that's why we have that. Now, the structures team talked about one important problem, and that's called the channel vent conflict for this project. So I'll take you back to the site location, but more specifically, we'll focus in on this area here. There was a channel running through our site, and what you'll see here is that channel running east to west, and a vent location represented here by these pile caps. Now, there's a 5-foot clearance between the pile caps and that channel. So I'm going to take you on a cross-sectional view here so we can get a more detailed understanding of the geometry. This is that cross-section, and what you can see here is the channel directly in the influence zones of that shaft. The problem here is that this channel, as it was constructed, was not designed to take the tremendous lateral loading that this shaft would be applying or transmitting to that soil. So after careful evaluation of our options, what we decided to do was extend our vent column down along our pile cap 10 feet to put the shaft, or the influence zone of that shaft, just below that channel. So that mitigated the problem. However, there is one more detail. Since we extended that vent column down, it's now embedded, and it now has a tendency to act like a foundation system itself. So what we did to reduce the lateral loading that that vent column would apply to the soil was we put a column isolator around it, and that reduced the problem. Now I'll hand it over to Shaibu, who will talk about underground utilities.
Utilities or existing utilities can affect construction and be one of the controlling issues as mentioned previously by Eddie and the geotechnical team. For our project site, the primary utilities that we had to consider were the 10-inch sanitary sewer running down Monte Vista Avenue to State Street, the 16-inch storm sewer and the 72-inch storm sewer on Brook Street, and we also had a 16-inch petroleum line and fiber optic line that was previously mentioned by the structures team. Our solution for the 16-inch petroleum line and the fiber optic line was to design our vent and abutments around it, around the clearance. But as you can see here from the foundation plan that Esteban mentioned previously, that we were unable to avoid the 60-inch storm sewer and the 10-inch sewer. Our solution for the 10-inch sewer was to relocate it to the east right-of-way. Our decision for this, or our reasoning for this, was because the property apartment on the east right-of-way would have been a lot less than the west right-of-way. And now Gonzalo will speak to you about our decision for storm drain design.
Then we take into the existing conditions of the storm drainage. As mentioned earlier, we have a 60-inch reinforced concrete pipe coming down all the way to the channel, passing water to the channel. We also have a 72-inch reinforced concrete pipe on Brook Street. Now there are three main areas that we focus on and actually drove our design. The first area right here, the intersection of Brook Street and Monte Vista, you have this 72-inch pipe, and it has pretty much a dead end tile cap here. So there are two different pipes, and the two catch basins connected. The other two areas, we found out that actually the 72-inch RCP deposits water into the Brook Street detention basin, and the channel itself has an outlet that deposits water into this basin also. So we went on to many alternatives, but we choose two main alternatives that we're going to go over. Alternative one is to shift the 60-inch RCP into the same right-of-way acquired by the sewer. Alternative two is underneath the railroad, so it's more about construction cost. Alternative two, which is the selected one, you have a 60-inch RCP connected to the 72-inch RCP into Brook Street. Now the main question is if we can do this. So that's why I'm going to give it to Shayu, and she'll talk about the design.
We analyzed the surrounding property to us into our 60-inch and our 72-inch connecting to Gold Avenue. We method to find the runoff from these properties, and then we plugged it into computer software to analyze the hydraulic line or the water surface elevation at certain points from Gold Avenue down to the 60-inch, 72-inch connection. Our conclusion was that our pipes could handle the flow demand for the entire length. And now I'll hand to Dan.
Thank you, Shayu. So now that we designed our grade separation, we need to know how we were going to construct it. So we broke it down into two construction phases, starting with our first phase. Phase one is going to consist of paving our State Street connector road, but not bringing access to the traffic. Next, we're going to join our 72-inch with our 60-inch storm drain sewage line. And when we do this, we're going to permanently block off Brook Street right here and create an access road for the residential area right here to get to Hope and to get to Monte Vista Avenue. In our next phase, we're going to we already have our State Street connector paved. So when we block off the Monte Vista Avenue to construct our overhead, we can, after we construct our overhead, we can then install our traffic signals on the State Street connector and open it up to traffic. So our overall improvements by constructing this project included that we met all of the city's required objectives. We also improved the safety of traffic and pedestrians in that area. We reduced the noise impacts and also the air quality in the area. And most importantly, we addressed the key issue of congestion, taking it from a level of service F to, at worst, a level of service C. And I'll take you to our cost estimate. We broke it down into very general sections. We have our structural steel and fabrication coming in as the most costly item for our project. Following behind that, we have our structural concrete for our structures and our retaining walls. Our total project cost is about $36 million. So there you have it, right? So now I'm going to pass it over to Zach Durek, who will discuss our lesson learned, and we're going to take off our hat as poly consultants and talk to the students and how we're going to change our whole major under this project.
Thank you, Dan. Thank you. I'll make this brief. As students, we really got to see that grade separations are indeed broad projects that involve a variety of disciplines. identifying the key constraints was really critical to our project. As a geotechnical engineer, I had some idea that there would be several problems with the project. Of course, we have our utilities running through the project, and of course that affected the structures through rent locations, which affected our foundations, which then affected, and well, you get the idea. So that was a key thing that we learned as a team, the different constraints that go into these types of projects. And secondly, and probably most importantly, we learned the importance of teamwork. We wouldn't have been able to do such a complex project without a great group of individuals, and we're very proud to present this presentation. Now, hand it back to Daniel just to give a few closing remarks.
Well, we want to thank our sponsoring agencies and companies throughout this project. And now we'll open it up to any questions you may have.
Are there any questions from the, in the back, way in the back there?
Yeah. I think you guys did a great job. Congratulations. My name is Franklin Corporation, and we're a roadway design and traffic firm. My question to you is, I see that you took into account the drainage downstream on Monte Vista. What about upstream?
We took into account that as well. If you may, we can go back to that slide. We use a rational method to ensure that our pipe could handle the flow that would be receiving once we connected all of our drainage to the 72 inch.
What about at the beginning of your vertical curve for your grade separation?
Our grade separation is down here,
Okay.
and we accounted for the runoff off the project site, and there's one pipe, one continuous pipe with head bases flowing from here down here. And these are all the project sites that affect the flow of this 16-inch pipe.
And I believe I want to touch on one more thing. You said that at the beginning of our vertical curve, on the both side, we had a low point at that point. We actually implemented 2 catch basins because we didn't want all the water rushing into the flooding the area.
How did you determine the length of your vertical curve?
From the Caltrans HCM power design manual, we had a 35 mile per hour vertical curve design speed.
How long was it? How long was your vertical curve?
We had 3 vertical curves. First one was about.
I think you have the profile.
Yeah, I didn't see stations on the profile. I just saw
It
the
doesn't have, I believe it doesn't have.
I don't. Yeah, it doesn't have any stations on it.
I think we have time for one more question, could we?
Question.
Pardon?
Is that failing? If I take this real quick, again, great work, very well done for design and where you're at. A couple of things on the finer points that as you work out in the industry, some of my more experience will give you some weak stuff. On the sizing piece, on the structure piece, there's just a couple of things real quick. You went with individual foundation to each column coming down to the bed gap. And post winter earthquake, I think we discovered that those columns can act as independent foundations. You want to tie them together at the pile cap as well as at the bed cap, so that they act as a unit and you avoid distributed damage in them. So that's just a minor point I wanted to point out. The same thing under bed design, you've got depths that are different lengths. And during the Northridge earthquake, we discovered that you can shift most of your damage, most of your force into your shorter depths when you do that, your shorter columns. So sometimes like you did an isolation around the one deck gap that's going to, we sometimes make longer columns. If you have equal column lengths, we get a better distribution during certain sizing. And you can isolate those from the drawings there. So kind of fine points that I just wanted to put out, otherwise I think it's great after that.
Thank you.
I think we're about out of time. We've got maybe time for one more question.
Yeah, just my name's Dudu with Caltrans. Just one question. When you, on your staging, you show code on Monte Vista,
Yes.
how would that impact the business? How long your codes are for?
How long? We didn't necessarily do how long our construction phasing. We didn't necessarily analyze that. but we would definitely have to mitigate for businesses to keep them open. So I guess not to make them mad or anything, disrupt their business flow. But that's definitely something we would have to take into account.
Your impact of the business. So that's one of the constraints you need to identify. How long the impact there. They might lose revenue. And those are pretty much main concern of the city that revenue driven taxes. So when you close it, short duration is much faster.
Real quick, what assumptions did you guys make on the right of way? Was the right of, did you assume the right of way was going to be acquired, or did the city already acquired the right of way?
The city, when we began this project, the city already acquired the right of way on the west side, but we actually chose our state street connector.
So did you assume that, or did you assume like you were in 2005 and the city had acquired the right of way?
A little bit of both. We look at the cost to acquire the land on both sides. The west side was less expensive, and the city, and we saw the city had owned part of it.
Is the 36 million include right of way, or just estimated construction?
It also includes
It includes right of way?
yes.
I believe it does not include the part the city already owns and we started.
Okay.
So
20% for construction management is too high. Don't get right, Doug?
They didn't have contingencies that was offsetting, but 35 million is about right for that. So that was kind of calls on the investment right away based on the synergies it did, so that's what we really did. That's what I was doing over here, the actual site.
So we have a couple of acknowledgements before we head out here. First, our advisors, Dr. Kitch, Mr. Nascimento, and Mr. Hudson over there. And we'd also like to thank Brandon Reyes, who also helped us out tremendously for our design in the civil team, and many other names that helped in the background as well. So thank you guys for your time, and hope you enjoyed our presentation.